Ah, making this video a second time. Yay. Yeah, maybe I can make it shorter this time. Oh, anyway. So on the speed of sound, again, the Hubris Hexac stock guy would post another remark, so I thought I would get to that. Kind of in a related way. I mean, my argument against what he's saying, I mean, he's bringing up speakers and using a little bit of math as a demonstration that, look, here's a proof that it's moving slower than the speed of sound, blah, blah, blah. And yes, the math makes it look like you're making an argument, but the math doesn't have anything in it. It's not the right equation. It's not the right formula for what you're stating your finding. All you're doing is making a time average, and it's not about the, you can't, if you cut a frequency into the bits that make it up, um, you're not doing justice to the actual what created the frequency or the wave. And we're talking about the mechanism that creates it, which doesn't perform the same way as the actual wave you get out of it. So the agitator doesn't have to be moving exactly the same way as the thing that carries the wave. So I'll get to that, but it's just a related thing. It was kind of coincidental, right? Because poorly applied mathematics, in terms of formulas, sort of reminds me of Miles Mathis, because he has this tendency to be unreliable in what formula he applies in his proofs. And he did this with his, pi equals 4 thing. He has this, he makes this argument that pi equals 4, and it's all based on the application of a wrong formula. A formula just does conversion, from like arc seconds to meters per foot or something, but it's not that. It's just a conversion formula. He was using it inappropriately to do the circumference argument when it comes to circular motion. And the circular motion, he was claiming, the answer came out to 4 instead of what it should be, pi, for the circumference. And it was just, because he was comparing apples and oranges, which are the, apple of say, a bicycle on a track or a runner on a track versus a planet going round in space. And the two circumstances are fundamentally different, as I pointed out, in that the runner has only one source of energy, which is his own motion, where the gravitational orbit thing is different because there's two forces. There's the acceleration of the thing moving, the velocity of the thing moving, and then the extra acceleration coming from gravity. So you don't have to slow down, so to speak, to go around a curve, where the runner has to essentially use his own momentum to do the curve. He has to essentially use some of his velocity to push himself around the corner, and so he has to slow down. All right. So anyway, but that's an argument already made. Blah blah blah. But anyway, it was just such kind of a glaring error to make, where you're not even using the right formula, and so this Hubris guide also does the same thing. So anyway, so it has to do with this speaker, and I've sort of been over this one before, I know, in previous videos, but can't hurt to do it again, maybe. Maybe it can't hurt. So he says, what about a membrane and a speaker? Alright, well, at least you got the membrane part right, but I don't think you're really understanding what a speaker does. And the whole function of the speaker is, again, a tension argument. It's like the tennis ball, or it's like a rubber band, or it's like a rope under tension. It's about tension, okay, tension. And nowhere in your math do you have a constant for the tension, which has to be in there. If you're going to talk about how the tension reacts to compressions and rarefactions, as Ken Wheeler would say. Yeah. Let's say the membrane can move 1 centimeter. Well, that seems insane. Okay, unless it's a really monstrous speaker. 1 centimeter is a huge amount of distance. So, little chance of that, I think. But anyway, amplitude A equals 0.01 meters. So he's loading his formula now that he doesn't explain. He just does the formula. He doesn't explain what formula he's using or why he's using it. So back and forth, and we apply a sine frequency of 50 hertz to it, which is hearable. So again, so now he's using the frequency number, and chosen one of a specific high number, because the way he's doing his math, the higher he makes it, the slower the speed will turn out, which is, you know, intuitively, oh, that's not right. I mean, it would be to most people. But anyway, you know, it's not that it would be to most people. I'm just saying it's an obvious flaw in your mathematical strategy that there would be any relationship between frequency and the speed of the membrane in a sense, because you're really talking about the speed of sound. Anyway, where t equals time. The velocity of the membrane is given by the derivative with respect to time, which is v equals dx divided by dt, which in turn equals 2 pi times 50 times a cosine of 2 pi 50 times t. So it's just two ways of saying the same thing. The dx dt thing was only talking about the amount of distance for this x component up and down divided by the time to go up and down, which is the velocity. But again, this is a simplification because you can't derive that without the constant, which is the tension constant. I don't know what they call it in regular physics. There is a word for it. But anyway, but you have to have one. Each substance is under a different tension, and you have to have that in there somewhere. It's like the density of water and air and all that. There's always got to be a constant that is going to put you into the right conversion. Anyway, since the maximum, of course, is velocity of membrane is given by the derivative with respect to time. Okay, so we did that part. Since the maximum of a cosine is 1, we get a maximum velocity of 2 pi 50a, which is approximately 3.14 meters per second. So he's just kind of time averaged the mechanism that creates the frequency in the membrane. So it's a little more complicated. Like speakers are actuated by a thing moving, and the speaker responds. You know, it's a reflexive thing. It's like pulling a. You can think of a stretched, like the Einstein fabric thing made out of rubber or something. You can just think about it pulling it down. The speed at which you pull it down doesn't really matter. It's when you release it and it does the boing, you know, the boing thing. That happens because of the tension in the medium that you're compressing. And so, like I said, there's nowhere in this math did you compensate for that. So you're just averaging the slowness of the what do you call it? The loading. The loading can happen at any speed. It's just so the only time that's relevant to the speed of sound argument is the point time of release and the time of complete expansion. You know, reflexive reaction to the compression. And that's all that's happening with a speaker. So a speaker just has a little solenoid in the middle, and a little steel rod in there, and the steel rod is attached to the speaker, which is under tension, which is inflexible, tight. It doesn't, you know, it wants to stay in one position. And you force it into a new position, like a rubber band, it will bounce back. So like a tennis ball, it's compressed by movement. So it doesn't want to go in either direction. It's rigid, firm, let's say. And it's designed to be that way. You can kind of look at it the way it's made. It's made to do this. It's little fibers and paper, or it's a fabric that's been starched. It's a, you know, you know, and it has even places in it where there's little relaxers which just create which buffer the frequencies. Anyway, so that number 3.14 meters per second is just averaging the up and down time first. So you're measuring too much of the wave you're measuring, because the only part of the wave that matters is the up part. And you're that's pretty much, you're taking something that happens real fast in one moment and including in it all the slow stuff that loaded it, and that's not fair. It's cheating. Alright, so it says this is not even close to the speed of sound, which is approximately 340 meters per second. Right, but it's just, your formula is it's a misapplication of a mathematical formula. And yes, it looks like you're making an argument, but you're really not, because you're using the wrong formula in the wrong way to measure something first that you're not even considering, which is, this isn't just about a frequency, this isn't just about the output, it's about what causes it. And again, I'm sort of trying to point that out, that you can't measure. It's like me pulling a whip back and then snapping the whip. If you did a time average over the slowness of my pulling the whip back and counted that, the part that rolls that creates the loop in the whip, so that's where I'm loading the whip, where the whip is, I shouldn't have to draw a picture, but when you pull it back, what you're doing is you're pulling an S into it, so that when you go forward, you're going to double the speed, like pulleys, because the one part's going to, for every bit one part moves, the other bit's going to move twice as much distance in the same time. You're creating a bigger circumference of the circle, so to speak, that you're going to pull the whip through. And so if you average the whole time, well, then the little thing isn't going to be going the speed of light, the tip, because you're taking the entire S and saying all parts of the whip are moving the same speed, and they're not. They're moving different speeds, and averaging the speed isn't going to give you the speed of the tip of the whip. And averaging a frequency vibration created by a mechanism that creates tension at one speed, it has to obviously be faster than the frequency you're trying to produce, but it doesn't have to be very fast, the pulling down of the speaker, and it's the release that's at the speed of sound, or faster, and creating the little sonic booms that end up being a sound because of the shape they're put through and how much echoing they do and all the rest of that crap, and the frequency of those vibrations. It turns out to be a sonic boom that is richer than just going bang, or boom. It has a pitch change and all that kind of stuff. So anyway, it's the frequency of the little boomlets that we're really hearing. But it's one mechanism that just happens. By regulating the frequency, you regulate what it sounds like, but it's really the same noise, sort of. So anyway, so the speaker works by this, pulling tension down and then releasing it. So it's like compressing a tennis ball and releasing it, or compressing a spring and releasing it. So you could have a spring that, you got to really push it down, and then when you release it, you only pushed it down 1/2 inch, but when you release it, the spring bounces up 4 feet. And that's what's happening with a speaker. It takes a lot more energy to pull it down. It takes a lot more energy. A lot more energy over a time period, pulling it down, and then it has to release it at the tension. The tension is what's going to release that energy very quickly. So it's the high tension of the paper with the threads in it, and the whole way it's been made to be very, it's probably a word for that. Stuff that, like paper, I could sit there and go flap with it and it doesn't do much. But if I took a piece of plastic and I flap it, it'll move much quicker because it's more rigid. So but this is just the law of sounding boards. I mean, in a sense, the speaker's kind of like a sounding board, but technically, it's a little more than that because there's this direct connection between the actuator and the speaker fabric. Without the speaker fabric, the actuator itself won't make much sound. So clearly, this speaker fabric is a necessary sounding board component, amplifier, if you will. But it's also the tension of that really creates the speed thing. I mean, a solenoid will only really make noises when you put it at a maximum and it starts bouncing. It'll bounce at a very high speed, and you'll hear that as like a buzz. But that's sort of getting into more complicated arguments that why everything makes a noise for a reason. And I'm just saying, if you really go look for the reason, you're going to find something moving faster than the speed of sound. And I just don't think you can come up with an example where it can't be explained that it's there somewhere. There's something moving too fast. So anyway, I think that's enough said. Yeah, I think so.